continue with what we were discussing in the previous lecture. So, in the previous lecture we were attempting to derive the energy equation. So, what are the steps that we followed? We first derived the total energy conservation, then we subtracted from that the mechanical energy conservation, and then we got the thermal energy conservation equation. That equation is written here with I as the internal energy. So, various terms, this is like the total rate of change of internal energy. This can be attributed to volumetric heating, surface heat flux and viscous dissipation. So, one part is viscous dissipation and this is pressure work or PdV, P dot del V, that is sorry, P into del dot V. So, P into del dot V, that term is there, which is just like the PdV work in thermodynamics. So, this is due to volumetric change whatever is the work done. So, that is P into del dot V and this is called as viscous dissipation. This is due to irreversible conversion of the work to overcome the viscous interactions into intermolecular form of energy. So, and we have shown that this viscous dissipation for a Newtonian and Stokesian fluid is always a positive contribution, that is, it always gives rise to heating and not cooling. So, the expression that we derived towards the end of the previous lecture, that summarizes to this expression. You can see very well that the viscous dissipation, this phi is called as viscous dissipation function. So, this viscous dissipation function is a function of basically the sum squares of the velocity gradients or rates of deformation. So, if you know the different rates of deformation, then it is sum of the squares of rates of deformation plus sum of squares of other terms involving the velocity gradients. So, velocity gradients are responsible for this term along with the viscosity of the fluid. Now, we will complete the derivation of the energy equation by expressing the internal energy in terms of enthalpy and then enthalpy in terms of temperature, because temperature is the measurable parameter. So, we should express the governing equation in terms of temperature. Okay. Now, to do that, the left hand side you can write what we have done is, see, this trick we will often play, we will convert as per our wish from a non-conservative form to a conservative form and then from a conservative form to a non-conservative form. So, in any of these cases we have to use the continuity equation. So, this is the continuity equation, this is actually 0 by continuity equation. Now you can combine these terms and write and combine these terms. So you can see that in one step we can convert the non-conservative form to the conservative form. Then what we will do, we will write the internal energy in terms of enthalpy. So H is equal to I plus P by rho, that is the definition of enthalpy. H equal to U plus PV, that written in different symbols. So rho I is equal to rho H minus P. So this becomes so we can club these two terms. These two terms, again I will not repeat, but what you can do is you can use the continuity equation to write it in a non-conservative form. These two terms correspond to the conservative form with enthalpy, plus you have some correction terms for converting internal energy to enthalpy. Okay. So these two terms together can be converted to a non-conservative form. How you do that? You simply use the product rule for differentiating these two terms and use the continuity equation. So if you do that, you will get rho the remaining terms will be 0 because of continuity equation. So this in a shorthand notation is rho total derivative of enthalpy. You are familiar with the capital DDT, that is the total rate of change is the change due to change with respect to time at a given location plus due to advection to a different location where you get a new velocity field and a new scalar field. Okay. So if this is rho dH dt, what these two terms together are? right. And this term you can write as minus P del U k del x k with an understanding that del U j del x j is equal to del U k del x k whatever. Del U j del x j is what? Del U1 del x1 plus del U2 del x2 plus del U3 del x3. So, it does not matter whether you use j, k, l, m whatever. So, why I have written it in this way is because this term gets cancelled with the corresponding term in the right hand side. Okay. So, when you convert the internal energy expression into enthalpy expression, the first observation is that the PDV work gets cancelled from both sides. So, you are left with the minus dp dt term from left hand side we have brought to the right hand side, it has become plus dp dt. Now, we will use what we will do is we will write this enthalpy in terms of temperature. So, in general what are the assumptions under which this is valid? We discussed it earlier. What are the assumptions under which this is valid? Simple compressible pure substance with no change in phase. So, you can write dH So, what is this? This is Cp. By definition of Cp, this is what is Cp. Now, we will write this using one of the TdS relationships, that TdS is equal to dH minus VdP. So, in place of dH we will write TdS plus VdP. Next, entropy is itself a function of temperature and pressure. So, you can write this as T So, if you compare both sides, then this term and this term, they have the same coefficient. That means this will be what? Cp by T, and this term you can write express by changing from entropy to a measurable quantity by using one of the 4 Maxwell's equations. So, if you compare both sides, now you can write this is basically coefficient of dP in both sides. Now, we know by the definition of volumetric expansion coefficient, beta is defined as this. So, volumetric expansion coefficient in qualitative form is what? Change in volume per unit volume for each degree change in temperature, and that has to be evaluated at some parametric condition. So, the condition is here constant pressure. So, you can write this one so you can write dH is equal to Cp dt in our expression. What we require is capital D dt of H. So, capital D dt behaves mathematically in the same manner as small d dt. So, the same expression can be used. So, you can write dH dt is equal to Cp dt dt plus so in the left hand side what is required is rho dH dt. So, rho dH dt is rho, you multiply by rho all the terms. So, when you multiply by rho all the terms, rho into specific volume is equal to 1. Now, you compare the left hand side and the right hand side of this energy equation, and we can observe one very interesting thing, that this dP dt and this dP dt, they get cancelled from both sides, right. This is in the right hand side and only this part, not this part. This part is still there, only this part with dp dt that gets cancelled. So, you are left with rho Cp this equation still is not mathematically closed. Why it is not mathematically closed? Because it has an unknown temperature, it has also an unknown heat flux. So, just like in Newton's law of viscosity, we expressed the stress in terms of the rate of deformation, here also we will express the heat flux in terms of temperature gradient, that is the constitutive behavior for heat transfer. Now, there are various mechanisms by which the heat conduction can take place. So, there is no single constitutive behavior for the heat flux. So, for the heat flux there can be different constitutive behaviors, but we will take as an example the constitutive behavior dictated by the Fourier's law of heat conduction. So, if Fourier's law is applicable, this is a very interesting thing, and sometimes beginners have a confusion on this. See, we are deriving an energy equation where fluid flow is also a part of the consideration. So, it is a equation, governing equation, the equation that we have written there is an equation for convection. However, for heat flux we are still using the Fourier's law of heat conduction, we are not using any other law. That means that actually convection is not a fundamental mode of heat transfer. The fundamental mode of heat transfer is still conduction, but in convection what at best you can say what is happening is advection assisted conduction or advection assisted by conduction, whatever. So, the basic heat transfer mode still remains conduction, because if you think of, there is a solid boundary and from the solid boundary heat has to reach the fluid before it is advected. That heat transfer from the solid boundary to the fluid is predominantly by, in fact is solely by conduction, because the fluid molecules adjacent to the solid boundary are stationary. So, the conduction is the only mechanism by which heat gets transferred from the solid boundary to the fluid, and then from the fluid one layer to the other by combination of conduction and advection. So, conduction is present in all occasions, and to calculate the heat flux we have to use the law of conduction. So, then this term becomes this term you can expand first in the non-conservative form. Even if you want to use the conservative form, you can use the continuity equation to convert it to the conservative form, just in the same way we did for enthalpy and internal energy, you can do it for temperature. So, this equation is the so called energy equation. That is the basic governing equation for convection. So, the left hand side is the total change in temperature. Again rho into Cp comes out of the derivative because of mathematical simplification, but not because of rho and Cp are constants. So, even if rho and Cp are not constants, they will still come out of the derivative, but they themselves may be variables. Right hand side, this is the volumetric heat generation, this is the heat transfer due to the surface heat flux, this is the viscous dissipation, and this is the pressure work. So, in this term you can see that for flows with negligible compressibility effect, this term is not important. Since in this particular course we will deal with incompressible flow, we will not consider that term to be any more important for the discussions and for the problems that we are solving subsequently. Okay. But wherever compressibility effects are important, that last term is important. Example of application. We will consider the example of first thermal boundary layer over a flat plate. So, first I will discuss about the problem qualitatively. Let us say that you have a fluid coming from first stream with a velocity u infinity and temperature T infinity. And let us say that the temperature of this wall is T wall, which may be greater than T infinity or may be less than T infinity. T wall equal to T infinity is not a case of our interest, because then there will be no heat transfer, because heat transfer is triggered by the temperature difference. So, we assume that T wall is not equal to T infinity. As an example, let us say T wall greater than T infinity. Example, you can consider even the other example. Now, as we have seen in fluid mechanics that there is a hydrodynamic boundary layer which grows because of viscous interactions, So, this is like 99% of u infinity and this thickness is delta, which is a function of x. This much we have understood while discussing about the hydrodynamic boundary layer. Now, what about the heat transfer? So, this let us try to draw a separate sketch for discussing what happens for the heat transfer. So, let us draw the plate. Consider a section. Here temperature is T wall, right. If you go further away from the wall, little bit away, the temperature is less than T wall. So, something like this. In this way, there will be a distance from the wall at which the temperature will almost come to T infinity, right. So, is it 99% of T infinity? Will the temperature of the fluid become 99% of T infinity? Which here is more, temperature of the fluid or T infinity? I mean, what is the lowest temperature of the fluid? In other words, the lowest temperature of the fluid is T infinity. So, temperature at any other location in the fluid has to be greater than T infinity for effective heat transfer from the wall to the fluid, right. So, the temperature where it asymptotically attains a value close to T infinity is not 99% of T infinity, but if you take as 1% gap, 1.01 of T infinity, right. So, let us say that this is 1.01 T infinity. So, this is for all practical purposes, this is as good as T infinity. Now, just like the velocity profile, you can also plot the temperature profile. One important caution, that in velocity profile we give vectors, arrows. In temperature profile, please do not give vectors, okay. So, because I mean all of us understand that temperature is a scalar and not a vector. So, do not give arrows, just draw simple lines without arrow. So, this distance from the wall at which the temperature attains practically T infinity, this distance is called as thermal boundary layer thickness. Just like the velocity where it attains practically u infinity is, that distance from the wall is called as hydrodynamic boundary layer thickness, this is called as thermal boundary layer thickness. So, now you have two boundary layers. In fluid mechanics we have just one boundary layer, so we talk about boundary layer. In heat transfer we have hydrodynamic boundary layer and thermal boundary layer. So, we have to distinguish these two by using these two different terminologies. The boundary layer in fluid mechanics, what we discussed, from now onward we will say hydrodynamic boundary layer, and the heat transfer boundary layer is thermal boundary layer. So, delta T, which is a function of x, is thermal boundary layer thickness. So, this thermal boundary layer as usual grows, so the delta T here is this one, and this line is the edge of the thermal boundary layer. Now, I will ask you the very elementary and basic question that should first come to our mind. What is the relationship between the thermal boundary layer thickness and the hydrodynamic boundary layer thickness? That means, can we say at least whether delta T is greater than delta, equal to delta or less than delta at a given x? How can we say? What is the scientific basis from which we can talk about that? So, to understand that, delta will depend on what? We have discussed it earlier. Delta depends primarily for a given velocity field. For a given velocity field, delta depends on which property of the fluid? Kinematic viscosity of the fluid. So, delta depends on nu. Similarly, delta T will depend on what? Alpha, the thermal diffusivity. Because more the thermal diffusivity, greater will be the distance from the wall up to which the heating or cooling effect of the wall will be propagated. So, just like kinematic viscosity is a messenger of momentum disturbance in the fluid, thermal diffusivity is the messenger of the thermal disturbance within the fluid. So, if you have the thermal diffusivity, that is K by rho Cp, K denotes the strength of conduction and rho Cp is the thermal inertia. So, it talks about the storage. So, conduction relative to the storage, that ability is dictated by the thermal diffusivity. So, thermal diffusivity in many ways is analogous to the kinematic viscosity. So, delta will scale with nu, I mean it will be related to nu, and delta T will be related to alpha. So, delta by delta T should be related to nu by alpha. These two have same dimension, meter square per second, same unit. So, this is a non-dimensional number called as Prandtl number. So, clearly depending on different values of Prandtl number, it is possible that delta T may be greater than delta, delta T may be equal to delta or delta T may be less than delta. For Prandtl number equal to 1, delta T and delta are identical. For Prandtl number less than 1, delta less than delta T, and for Prandtl number greater than 1, delta greater than delta T. So, with this little bit of qualitative understanding, we will now derive the thermal boundary layer equations. thermal boundary layer equations over a flat plate. So, we will assume steady flow, incompressible flow, so for incompressible flow the last term is not important in the energy equation. Steady flow of course will mean that in the left hand side the time derivative term will be 0. We are neglecting any volumetric heat generation and we are neglecting the viscous dissipation. We will separately talk about certain problems later on where viscous dissipation is important. Normally for flow over a flat plate with open ambience the viscous dissipation will not be important, because viscous dissipation depends on square of the velocity gradient. So, if the velocity gradient is very large then that will be important. So, in very small confinements if a fluid is constrained then viscous dissipation may be important. So, we will talk about some such examples in this course, but for flow over a flat plate we will assume that in general viscous dissipation may not be important. So, with this we will write this equation in the boundary layer coordinates. The boundary layer coordinates, x, y coordinates we have discussed that what is the boundary layer coordinate. So, with the boundary layer coordinate so the left hand side this term is 0 because it is steady flow. This term becomes u del t del x plus v del t del y. Now, to proceed further we need to make a simplification, and the simplification that we will make is that k is a constant. See, we are not bothered about whether rho Cp are constants or not, because anyway that is coming out of the derivative, but to bring k out of the derivative we have to assume that k is a constant. So, we will make another assumption that k is constant, that is the thermal conductivity of the fluid is constant. So, if you do that and then divide this k by rho Cp you will get the alpha in the right hand side. So, your equation will become now this equation we can say that it is the energy equation for heat transfer for flow over a flat plate, but in terms of boundary layer consideration, the boundary layer consideration for hydrodynamic boundary layer, what was the important consideration? Delta much less than x. Here we will assume for thermal boundary layer theory that delta T much less than x. So, now what is the order of magnitude of this term? Yes, this is del x of del T del x, that means some characteristic temperature difference by some square of characteristic length. What is the characteristic temperature difference? T wall minus T infinity, we will call it in a short notation delta capital T, where delta T is T wall minus T infinity divided by L square, and so x characteristic is L for flow over a flat plate, and this is what? So, out of these two, which one is more? Clearly this is the dominating term. So, we can neglect this as compared to this. So, that gives rise to the thermal boundary layer equation. So, let us summarize the hydrodynamic and thermal boundary layer equations for flow over a flat plate before we solve these equations together. Remember that our philosophy in forced convection is that the velocity field is already known. We will use that velocity field to obtain the temperature field. So, the difference between the boundary layer momentum and energy equation is that this equation is what? Linear or non-linear partial differential equation. This is non-linear partial differential equation because of these terms u del x like that. But the energy equation is linear in T because u is a separate function which you can get from the momentum equation solution. So, once you get u, then it's linear in T. So, you can solve for the temperature. Now, it is very tempting to look into the similarity of these two equations because you see as if u is replaced by T and nu is replaced by alpha. So, if we consider a situation, if nu is equal to alpha, that is Prandtl number equal to 1, then what happens? If Prandtl number equal to 1, these two equations are the same, basically same form. So, the question is, will the solution be same? So, this is what Reynolds was thinking about. See, Reynolds was a very clever scientist, mathematician, whatever you call. Reynolds did a lot of work in fluid mechanics, and his first thought was that how will I solve the energy equation? So, one possibility is that can I solve the energy equation without solving it? It appears to be a kind of paradox that how can you solve an equation without solving it. So the possibility is that can I look into the analogy between these two equations, and then using that analogy from the solution of this we can directly tell what is the solution of this without solving this equation. And when Reynolds attempted that, that led to a very famous derivation in heat transfer which we will do now, is known as Reynolds Analogy. Now question is, when you have the Reynolds Analogy, you also have to make sure that these equations are analogous not just in terms of equations but also boundary conditions. So what are the boundary conditions? So this is the flat plate, this is the y axis. At y equal to 0, what is the boundary condition? U equal to and T equal to T wall, and the other boundary condition at y tends to infinity, U tends to U infinity and T tends to T infinity. So see, although for Prandtl number equal to 1 the equations are same, but the boundary conditions they do not look the same. For example, it is a homogeneous boundary condition, it is a non-homogeneous boundary condition, and these values are different. So how can we convert these equations in such a way that not only the equations look similar, the boundary conditions will also be the same? The answer is very simple. You renormalize the variables, that is, you define a new variable so define okay. Always remember one thing, I mean these are intuitive things, but sometimes we do not give a thought to it. When you define non-dimensional temperature, do not define T by T infinity like this, because it is the temperature difference that drives the heat transfer and not the absolute temperature itself. So non-dimensional temperatures are normally defined based on the ratios of temperature differences and not temperatures. Okay. So non-dimensional velocity U by U infinity, but non-dimensional temperature not T by T infinity. Okay. Because it is the difference in temperature that drives the heat transfer. So now the boundary condition at y equal to 0, U bar equal to 0 and theta equal to 0, at y tends to infinity, U bar equal to 1 and theta equal to 1. And if you cast that equation, this is a very small exercise but I will leave it on you, you can just show that this equation will boil down to U bar del x So what you can do is you can change the variables from U. So you also define V bar is equal to V by U infinity. So you change the variables from UV to U bar V bar and from T to theta by using these definitions in that equation. You will get equations again in the same form. It's very little algebra, nothing is there to show this, even by observation you can say. So then now we are in a position that the governing equations and the boundary conditions are exactly the same. What are the variables? Variables are u bar and theta. So, we can say that since governing differential equation and boundary conditions are same in form for u bar and theta, we can conclude that u bar is equal to theta. This is something which is not very intuitive, because this is a solution of a nonlinear equation, this is a solution of a linear equation. So, some mathematical insight should get into that. We will not be too much bothered about that, but we will see what is the consequence of this. So, this is u by u infinity is equal to T minus T wall. Again I am repeating that as an engineer we are not so much bothered about what is the temperature, what is the velocity. In fluid mechanics, what is the most important parameter? The wall shear stress that we are bothered about, and in heat transfer, what is the most important parameter? Wall heat flux. So, wall shear stress in fluid mechanics and wall heat flux in heat transfer. So, and you can see that both will follow one from the other by differentiating this with respect to y at y equal to 0. So, we will differentiate both with respect to y at y equal to 0. So, what is this? This is tau wall by mu, right, and what is this? Minus wall heat flux by K. Q is equal to minus K del T del Y. So, 1 by mu u infinity tau wall now tau wall we can write in terms of skin friction coefficient Cf. So, tau wall is equal to Cf into half rho u infinity square. And wall heat flux H into T wall minus T infinity, right, where H is the convective heat transfer coefficient. So, we can write 1 u infinity will cancel here, Cf by 2 So, we can multiply both numerator and denominator by L. So, what does it become? What is this? Nusselt number based on the length L, and what is this? 1 by Reynolds number. for this particular problem we can also write this as Nusselt number by Reynolds number into Prandtl number. Why? Because we assume Prandtl number equal to 1, then only these two equations are the same, nu and alpha are the same, or Prandtl number equal to 1. So this is actually equal to 1. Why we are doing this is because Nusselt number by Reynolds number into Prandtl number has a very interesting physical interpretation. What is that? Prandtl number is mu Cp by K. So mu gets cancelled and K gets cancelled. What is this? You just multiply both numerator and denominator by delta T. You will get a physical meaning. What is this? This is convection heat flux and this is axial advection. This is heat transfer due to fluid flow along x direction. So this you can say that convection flux by axial advection flux. Because these are all non-dimensional numbers, this ratio is also a non-dimensional ratio which is called as Stanton number. So we can write that Stanton number is equal to Cf by 2. This is called as Reynolds analogy. The beauty of this analogy is that for fluid mechanics, if you can find out what is Cf, then you can say what is the corresponding heat transfer parameter without solving anything. But this being a very beautiful and simplistic expression, there are major assumptions associated with that. So what are the major assumptions associated with this Reynolds analogy? The most important assumption is, first of all, there is no pressure gradient. If there is a, that means it is flow over a flat plate. If there is a pressure gradient, then you will have an extra pressure gradient term in the momentum equation, then there will be no analogy of the momentum and the energy equation, right. So there is no pressure gradient, that means flow over a flat plate and Prandtl number equal to 1. These are two very major assumptions. Other assumptions we have already written for the boundary layer derivation. What are the assumptions? Like for example, steady flow, incompressible flow, constant thermal conductivity, negligible volumetric heat generation, negligible viscous dissipation. So all those are there as assumptions, but two prima facie assumptions which are a must and which are very strict. One is that there is no pressure gradient, that is flow over a flat plate, and then Prandtl number must be equal to 1. So Prandtl number equal to 1 and del P del x equal to 0. These two must be satisfied. So this Reynolds analogy is very nice, but it can be applied only with Prandtl number equal to 1 in addition to the assumptions that we have considered. So the situation is that when Prandtl number is not equal to 1, what happens? We will discuss about that in the next lecture. Thank you.